going to start with the etherist. Why? Because there's some loose ends that need to be connected, I guess, tied up. And so I'm going to start there. And in order to start there, I need to start with the kindergarten physics, because some of these people have not gone through kindergarten physics, but they want to do college level physics. They want to talk about their theories, their great theories, whatever they thought about. And they don't know the basics. They don't know kindergarten, what they're supposed to do. The kindergarten side. They never played with blocks. Okay, and we need for them to come back to kindergarten, play with blocks, and understand the basics of physics before they can move on. Okay, so let's start with the kindergarten method. I'm sorry for those of you who already know all this stuff. It's probably boring, but I need to cover these loose ends on the one hand, and it's a refresher for those who know it, okay? So here it goes. Okay, so here we have, this is physics kindergarten, okay? We're going to be doing this, and the first rule you have to understand is that what they do today is known as the mathematical method. They've been doing it for the last 400 years, more or less, since the 17th century, so-called scientific revolution. And this is what it's all about, or what it's come down to today. It says the purpose is what? To persuade, convince, convert, and recruit. That's what the whole method is all about. And making money, becoming popular, hitting the bright lights, etc. What is the mathematical method? Well, it consists of observation. They observe. You observe something happening. You do an experiment to repeat the observation, more or less. This is just a sketch, right? Skeleton of what they do. You measure, especially the visible objects, because you can't measure the invisible ones, the untouchable, unseeable, right? And you describe the motion that you observed or that you measured with an equation. You propose the most irrational explanation you can imagine, because that's what they do. They use concepts as physical objects. They use words such as field and energy and mass when they should not be using that for a physical interpretation. And they ask their colleagues to challenge the findings, to confirm the fellow's findings, the person who did the work. And then if more than 50% of them, of your colleagues, agree with you, then it becomes a theory. The hunch, the speculation suddenly morphs into a theory. And if more than 90% believe in it, then the theory becomes a fact. And so that's how you end up with, I guess, the flat earth society. Everybody votes for it, and so it becomes a fact. And then you go on to a talk circuit and win prizes. That's the mathematical method. That's what we see today out there, okay? And so we're trying to contrast against that the scientific method, which none of these people have discovered in the last 400 years. That's what we do here. We do the scientific method as it relates to physics, okay? So here it is. This is the scientific method, okay? The purpose is to explain rationally, okay? Very straightforward. And we do what is called a hypothesis. That's the first step, okay, of the scientific method. People out there who I call idiots. Idiot is an individual with big ideas. There you see the definition at the bottom. These people call it semantics, word salad, waste of time, etc. No, you must do the hypothesis. You have to tell us what your assumptions are. And the assumptions include the following, include the objects, the things that are going to play a relevant role in your theory, okay? Unless you introduce the objects first, we will not understand your theory of physics. Okay, so you need to start with the objects. You need to point to them and say, look, this is a tree, this is a rock, this is a stone or a house or whatever. And you point to them, and once you can get past that step, you can go on to your theory. But until you can point to the objects and define your terms scientifically, meaning that you are able to defend your definitions against attacks. Okay, people are not going to like your definitions maybe, and so you're going to have to be able to defend them. So you need to point to the objects, you need to define your words in such a way that you can use them consistently, rationally, scientifically. And then you present the statement of the facts, what we call the initial scene, first frames of the film, okay? So that we know what your starting point is. You need to point to that first frame of your film. You can't do it like they do it with Big Bang, that they start at the second frame. No, we need to know how the singularity came to be, and that's the first frame. Or, you need to show that process. And until you got that, you don't have a movie. You can't start at the second frame in a movie. And then, yes, you can move on to the second step, which is theory. In other words, the explanation of a cause, of a mechanism. And finally, you end up with conclusions. Okay, that's how we think the scientific method should be done. If you have any objections, well, you have to put them, you have to explain why. What objections you have, specify, fight it. I have no problem with people fighting it, but that's the scientific method. You don't like it? Well, make your case. You're in a court of law. Okay? Okay, so here we have the issue with the etherist. And, what we know is that, you let go of a spoon, for example, right? And it falls to the floor. Spoon is made of molecules comprised of atoms, okay? So we're just going to look at one atom of the spoon and one atom of the earth. Any atom that you want, inside the earth. And for some reason, the atom of the spoon is attracted, it's absorbed, it's pulled, whatever you want to use, by the atom in the center of the earth. You want to use push, no problem. Something maybe is pushing the atom of the spoon against the earth. Either way, no problem, okay? But we have to explain the process, the mechanism. Why does one atom approach another atom? That's what we're trying to figure out here, okay? We call that process, that phenomenon, we call it gravity. You want to call it X, no problem. We call it gravity. One atom is attracted to another atom. We have to explain why. What caused that atom to approach the other atom? Okay, attraction, okay, that's, could be push, no problem, but you got to explain the process. Okay, that's all we're saying here. Okay, so here we have two atoms, our two atoms. You can say one belongs to the spoon, the other one to the earth. You can say one atom belongs to whatever, a feather, an elephant, the other one to the sun. I don't care. But we have two atoms. One's going to approach the other atom. We have to explain what causes one atom to approach the other atom. Okay, that's the starting point. That's what we have to explain. Okay, and so that's the question. Okay, we need to find out if there's something in between there. Okay, perhaps. Maybe something on the outside pushing them in. Fine. Everybody's got their own theories. Okay, so that's what we're going to try to explain. Okay, we got that? And I put them sideways, but you can put them up and down in any direction you want if you want to explain gravity, for example. No problem. Because after all, the Earth is on the ecliptic of the sun. The atoms are on the same level, and you could say they're sideways. They're not up and down or like we are here in Earth, towards the center of the Earth. Okay, so how does quantum mechanics explain this type of thing? Well, they go through light. They try to explain light and how light is manufactured by the atom. Okay, that's their starting point. And what they do is they try to explain gravity, but they can't. Okay, and you'll see why. Okay, here it is. Okay, this is their version. They have two atoms. The atoms are the planetary atoms. That's what they use. They deny it. They constantly deny it, but that's what they use because that's what they're going to use for ionization. They're going to use it for quantum jump, and they're going to use that atom for electricity. They're going to talk about the bead, electron bead, going from atom to atom. That's their version of electricity. So yeah, even though they deny Bohr's, Rutherford Bohr, right? Quantum atom, the planetary atom, that is exactly what they're going to be using for their explanations. That's the one we're going to use here. If someone has a different atom, he's got to put it in there, right? So what is it? They say that when the electron bead goes from different energy levels back and forth, by doing so, it emits and absorbs energy. Energy is mediated or illustrated as waves of light. We're creating light, electromagnetic waves, okay? And as you can see, the waves go outwards, okay? And the question is, if they go outwards, how does that pull? because the atom is shooting that thing out. It does absorb also, but we don't know if it's from the same atom that's that it's trying to attract. Okay, so all we know is that each atom is throwing electromagnetic waves called energy in every direction radially, and by shooting it out, we don't know how that pulls anything inwards. So that's one problem. Another problem, again, is the atom, and then there's another atom, and that's another problem, which is the wave. Okay, and as you can see, you see a bunch of arrows there. Here, let me point that out a little clearly. Okay, this is what you're seeing. You're seeing what is known as an electromagnetic wave. And what is an electromagnetic wave? Well, it consists of vectors and electric fields. The field is that whole thing. For example, one of those, the red group of arrows, those are called the electric field. And the blue ones here are called the magnetic field. Okay, what is a field made of? Vectors. What is a vector? What is a field? Well, there you see it at the bottom. Field is a quantity. Okay, and what's a vector? Another quantity. So both of these are mathematical terms. Both field and vector are mathematical terms. They have nothing to do with physics. They're just descriptions, numerical descriptions. So what I'm saying here, you cannot use this so-called wave, you cannot use the field, you cannot use the vector to give a physical interpretation to a phenomenon. You cannot use that to say that gravity is a wave, or gravity is a field, or gravity is a vector. You cannot use that way because these are all mathematical concepts. They have to do with measurement and with pre-established standards. Okay, so we cannot use these concepts, these abstract concepts to do, you can't pull on a donkey with a vector. You cannot pull on a donkey with a field, and you cannot pull on a donkey with a wave. Now, if you want to pull on a donkey, you got to put a rope maybe around its neck, or I don't know, a tie wrap. Pull them in. Okay. Okay, how do we do it in science? Well, in science, we put a physical object to explain the physical mechanism. Okay, that's what we're interested in here. And here you see our model. We're saying, look, we have the quantum jump, no problem, but it's a shell that is expanding and contracting. That's what we say the atom looks like. It's a ball. Okay, it's like a balloon. Okay, I hope that's clear there. You have the 2D model on the left, the 3D model on the right. Light is torsions of a rope that connects these two atoms. Okay, and so as they expand and contract, they torque the rope. That's light, and that's quantum jump, all in one shot. What you're staring at is a physical entity. Okay, we're not talking about abstractions. We're not talking about concepts, mathematical concepts. We're talking about physical entities. We're saying the atom, hydrogen atom, is a ball. Okay, so there you have two hydrogen atoms. They're pumping back and forth. They're torquing the rope that interconnects them. And here's the construction of this thing. Okay, you will see it here in a second. Rope turns into the threads of the rope, right? Two threads of the rope turn into, one goes through the center of the atom and forms the proton star, and the other one loops around, produces the electron shell, okay? The electron membrane that encapsulates the proton star, okay? And there you see more or less what it looks like. You can see the rope on one side and the thread, the electric thread going to the center of the atom, okay? So this is our model. So the atoms and the rope are constructed of the same threads. There's no difference between them. Okay, so that's our model, and you can see it's all physical. We're talking about a rope. We're talking about two threads, or a rope made of two threads. What's a thread? Well, if you don't know what a thread is, ask your grandmother for a needle, to sew your pants, and she'll put a thread through it, and that's a thread. Okay, so some people say, oh, a thread is a concept. No, a thread is an object. Okay, it looks more or less like this. This is a big thread, okay, a thick thread, but it would look something like that. It's an elongated object. Okay, so a thread is a physical object. Our thread is three-dimensional, very thin, very short, very, narrow, right? But it's 3D. Okay, and so is the rope, so is the atom. So we're talking about all 3D stuff here. We're just saying it's very thin, And just like we can't see atoms, much less can we see the rope, which is much thinner than, the diameter of an atom. Okay, so here we have the electromagnetic wave compared against the rope, and you can see why they've mistaken it over all these years. It looks pretty much the same way, except that they're talking about concepts, they're talking about waves, fields, and vectors, and here we're talking about two threads. And we gave them the same name, electric thread and magnetic thread, just to keep with convention. That's the only reason we use the word electric and magnetic. There's no difference between the threads, except that one torques around the other, or twines around it. Okay, but there you see it, and we say that it's a good thing that we can show that the wave equation, C meaning the speed of light, equals frequency times wavelength. That means when you increase frequency, you reduce the wavelength, and vice versa. And to the lower right there, you see why, because you take any rope, the more you torque it, the shorter the links, okay, and the more links that you can put for a given length of rope. Okay, so we think we're in a pretty good ballpark of what's out there, of what Mother Nature uses out there. Okay, and so here we have back our two atoms. Okay, and the question is, what is an etherisk going to put in there? The quantum mechanics, they put in there wave, fields, vectors, right? Those are concepts, so we don't accept them in science, in physics, to give a physical interpretation. We put a rope. What is the etherisk going to put in there? Well, hopefully they put some ether in there, whatever ether is, okay? So let's find out what it is. Okay, so people say, Bill, you don't know what the ether is. Why? Because every time they ask me for the ether, this is what I put up there. That's the ether. Bunch of particles. That's what it's always been. Nothing different than that, okay? And these people say, no, Bill, you're misrepresenting the ether. That's not the ether. What can we do with particles? Okay, no problem. Call it something else, but if you want to use the word ether, I'm not going to object either. It doesn't matter to me. But this is what the ether has always been, okay? Why is it? Because they've always thought, at least since the 17th century, since the days of Robert Hooke, who was the guy who discovered that light has wave properties. This is what they thought of it, at least in the 19th century. They thought that the ether, the bunch of particles, were what light was made of. All these, you can say the electromagnetic wave was made of particles. What else was it made of? I mean, what is a wave other than vectors? It's either vectors or particles. Physically, they were thinking of particles, okay? And of course, you had Michelson and Morley. They ran a series of experiments, really, to try to show whether the ether existed or not. And to their satisfaction, or to a lot of mathematicians of those days, researchers, they concluded there is no ether. Why did they conclude that? Because, they looked at the ether as an ocean of particles. And they said, well, look, the Earth is moving against the ocean of particles, against this ocean, like a fish moves against an ocean. Or like the Higgs boson, the Higgs field. What is that? A bunch of particles, and a fish is moving against that. The little particle fish, right? And some go swiftly through it, and some go slower. That's Higgs in a nutshell. That's what they claim to have proven for mass. Okay, great. And the ether was more or less the same thing. You had the Earth moving in this ocean called ether, bunch of particles. And of course, there should be a difference if you move against, the particles than if you move, in a different direction with respect to the particles. Okay? And what they showed, to their satisfaction at least, is that light does not change its speed whether it goes against or sideways or in any direction. And Einstein came a few years later and he said, look, I think I've figured it out. Light travels at the same speed all the time, irrespective of the movement of the source of that light. Okay? And he was totally right. The only problem is that Einstein couldn't explain why that was the case. How can you explain that physically? Mathematically, they just wrote an equation. How do you prove that, or how do you explain that? How do you explain that mechanism from a physical point of view? And yeah, I showed that the other day, so I'm not going to go through that again. But yeah, we can explain that very easily with a rope model. The atoms simply slide through the rope, and that's why it doesn't add to the speed of light, the torsion of the rope between two atoms. Okay, that's in a nutshell. Okay, so where did I get all this? One fellow asked that question. He said the following. He says, when was the ether declared to be particles in history? And my answer is Greeks. You know, the ether was air, and air, everybody thought of air as particles. You know, even to this day, what do you think of air when somebody says you're breathing air? Well, you're breathing a lot of molecules, and each molecule is made of atoms, right? And there's all kinds of garbage in the air, so you're breathing all those particles. What is the air? Air is particles, and that's what the ether was. The ether was the air of the gods, the particles that the gods breathe. That's more or less the notion. It has your own threads, ropes accurately describe the properties of ether. No, our threads have nothing at all to do with a bunch of particles, which is what the ether was. So if you're going to talk about the threads in terms of ether, we're going to use the notion that everybody understands by ether except the ethers. Okay, the ethers are the only people who don't know what the ether is. But everybody out there knows what the ether is. It's a bunch of particles. And no, the threads are not made of discrete particles. The thread is made of a single piece. It's a flexible, single piece thread that builds all the atoms and all the ropes that interconnect the atoms in the universe. Okay, so no, it has nothing to do with the ether at all. Okay, so where did we get this? Well, we got it from this fellow, or one of these fellows. This is Aristotle there. He's on the left, if you don't see him down there at the bottom. And yeah, this is what they thought. They thought that the Greeks, they thought that the ether was this air that the god breathed out there in the dark night. You know, they couldn't see it, and they say, yeah, but there's something out there. And so they said, what covers everything here on earth? Well, it's the ether. So the ether somehow became, you know, this universal body of particles that the gods breathe up there in the Olympus, okay, Mountain Olympus. So that's more or less the notion where it came from. And people say, Bill, you're full of it. Okay, so let's prove it to them. Let's prove. They want proof. They want evidence. Okay, let's do that. Let's do a little proof and evidence. Here it is from the Wikipedia. From dictionary.com first. Ether, the ancient Greek, what? Personification of clear upper air of the sky. What was it? A bunch of particles. That's what it was. That's what they thought of it. Here's the mythological origins in the Wikipedia. It says the word ether, you know, in the Homeric Greek means pure, fresh air or clear sky. Okay, and it was thought to be pure essence of the that the gods breathed, filling the space where they lived, analogous to what? The air breathed by mortals. So ether means air. Okay, and air is made out of particles, so they thought of air of the ether as many particles. And there's another comment there in the fifth element in that same article for the ether. It says, speaking about air, what is it? Air, right? Plato mentions that there is the most translucent kind, which is called the name of ether. Okay, so what is ether? Ether means air. Okay, it's just another word for air. And air is made out of particles. So there you have it. Very simple, straightforward. All those people who call themselves etherists and they say it's not a bunch of particles, then they don't know what the ether is. The ether has always been a bunch of particles. That's the definition of that concept. It's not a physical object. Okay, a bunch of particles does not an object make. What makes an object is shape. You point to the table and you're not pointing to every atom that makes the table. You're pointing to the whole thing, the whole shebang, and call it table. Same with a rock, same with a tree. That's the way you got to look at the ether. The ether is the whole shebang. And if you want to talk about a portion of what it's made out of, you know, mereology, that's got nothing to do with physics. That's got to do with a religion known as mereology. Okay? It's got to do with what philosophers do, which has nothing to do with physics. They call themselves philosophers. Okay, one fellow says, okay, here he is. He says, I never said the ether was an object. Okay. It's a physical substance nonetheless. See, the word substance and the word object are perfect synonyms. There's no difference between them in physics. Now, we're not talking about ordinary speech. Over there in ordinary speech, they have all these words, and there's nuances in the definitions. In physics, it's black or white. It's either has shape or it don't. Just that simple. So the word object, the word substance, thing, body, entity, all those are synonyms, perfect synonyms. No difference between them. Okay, so he can't say it's not an object, but it's a substance. No, not in physics. In physics, substance and object mean exactly the same thing. So obviously he hasn't gone through kindergarten physics and he doesn't understand that. Okay, so of course it has no shape. Well, if it has no shape, it's a concept. It's black or white. It either has shape and it's an object, or it don't have shape and it's a concept. Okay, you can't see its shape. But if it don't have shape, then then you can't see it. Obviously, you can't see its shape. Meaning it does have shape, but you just can't see it. I mean, what's the issue here? Okay, so this is where we have a little bit of contradiction. Now, a lot of people make this contradiction. That's why I'm putting what this fellow said up here, because it's kind of a didactic tool for all those, to use against all those people who vouch for the ether and they don't even know what they're saying. Okay, so he says the shape is defined by a container, meaning it does have shape, because you can shape it, you can mold it to whatever you want. And that's absolutely wrong anyways, okay? It's not true, okay? But he thinks it's true. He thinks that water has shape only because it's in the glass container in your cup or whatever, okay? Not true, okay? Water had shape before you put it in your, in your container. It's like any other type of fluid, like space. Oh, space is a fluid. Yeah, and he says that space and ether are the same thing. So this is one of those fellows who says space and ether are the same thing. Other etherists say, no, space contains ether, like if ether was a bunch of particles that are put into a container called space. So they have these differences as well. You got to find, all these etherists, they don't agree. They should have a powwow and resolve their differences before coming here. It takes on the shape containing it. Again, he thinks, a bunch of particles, a bunch of molecules, a bunch of atoms, they don't have shape on their own without something constraining them. This is their notion. Okay? They have this squeezing, this pressure idea in their minds that you need to contain somehow the particles in order for them to have shape. And no, anything made out of atoms, an atom has shape, anything made out of atoms had better have shape. Whether there's a container or not, it already has shape before you put it in the container. And they don't understand that anything made out of atoms had better have shape. Ether has the shape of the universe. I love that one. Okay, what is the shape of the universe? Please draw the universe so we know what the shape of ether is. So he constantly contradicts himself. On the one hand, he says it doesn't have shape. Then it says the shape of the container has the shape of the universe. And all we want is for him to draw a picture of the universe, of the container, or whatever, We need a picture of the ether, okay? And he says, does air have shape? Does water have shape? No, they don't. Oh, my God. So, again, this poor fellow has never gone through kindergarten physics. But he has strong ideas about the ether. Okay, so let's show him that, yes, absolutely, air does have shape. And water does have shape, or liquid, any fluid for that matter, has shape. Anything made out of atoms have shape. Let's illustrate that for him. Here we have an astronaut, and he's going to pop a balloon in the middle of space. And that balloon contains some air, or whatever gas you want. As long as we can color code it so that we can take a snapshot of it. And I want you to tell me if you see some kind of shape floating in space here. Okay, here it goes. Okay, that's the air that the fellow released. Here you're going to see how he pops the balloon. Okay, he's going to pop the balloon. Okay, and the air comes out. Does that blob of air, does that have shape? Does it have a container? It's in the middle of space. I don't know what container you think it has. Okay, now you may not like to think that their particles can be without a container, but you have the air on Earth. The air on Earth covers our planet because of gravity. Something we call gravity, a process, a phenomenon we call gravity. And that air does not leave the planet. It just stays all around the Earth, for those who believe in the round Earth, okay, and the spherical Earth. That air has nothing on the outside pushing it in. And the question is, why doesn't the air that's covering the Earth, all that atmosphere, why doesn't it just leave and go to another planet? That's what you got to answer. And same here. You can see that the balloon popped, all that air came out. If you could take a snapshot of that, okay, you would say that thing, that whole blob has shape. Blobs have all better have shape. And people say, well, but it changes from one moment to the other, it changes its shape. We're not talking about the whole movie. We're talking about one frame in the film. Just one frame in the Universal film. Does that, is there something in that frame that you can point to? And if you can, we call that air, that bunch of molecules together, the whole blob, we call that shape. It's got shape. Okay, so yes, all liquids, all fluids, all have shape. Okay, it's concepts that don't have shape. Okay, like plasma. Plasma doesn't have shape because plasma cannot stand still. You can't take a snapshot of plasma because what you have is gas. Okay, so here you have the same astronaut. He releases a blob of some liquid. Does that liquid, that blob, have shape? And hopefully you say that it does. Okay? And so if you say that it doesn't, then you got to see an ophthalmologist. You got problems with your eyes. Okay, so here we have this fellow, and he says the following. He says, I'm saying the ether is a continuous fluid. Yeah, fluid is a concept. You're just saying what the ether does. You're not saying what the ether is. Okay, so to say it's a fluid is like saying water is fluid, oil is fluid, molasses is fluid. Great. And what have you said? Yeah, they're fluids. They're, they're liquids, semi-liquids or whatever. You haven't said what molasses is. You haven't distinguished molasses from oil from water. That's the issue. We need for you to put ether there next to those and say, this is the ether and that's how it's different than molasses. Otherwise, I'm going to say that your ether is molasses. I have all the right in the world because you're saying it's just a fluid, it's a liquid, it flows. That you're just telling me what it does, and so does molasses. So I can put molasses and say, okay, so you're saying the ether is molasses. How does that pull on anything, or how does that cause gravity? Okay, so I'm in my right, and until you can fix that, until you can show us a picture of your ether, we won't know what you're talking about. Okay, it says a substance such as a liquid or gas that can flow. And again, it says a substance. The first thing is a substance is an object, is a thing. In physics, they're all the same words. Okay? Something, thing, object, substance, body, they all mean the same thing in physics. It either has shape or it don't. If it don't, it's a constant. That's simple. Okay? So if it's a substance, don't tell me that ether is not an object. You can't have it both ways. You can't say it's an object, but it ain't. Okay, this is what they do. They go back and forth because they haven't taken kindergarten physics. They say, oh, you're talking semantics, Bill. You're doing word salad. There's absolutely no reason why the ether can't be fluid. Okay, no problem. We're not criticizing that. We're saying draw it. Make a picture of it so we know what you're talking about. Okay, remember, what was the first step? Object. You need to present the objects, the actors in your theory. Hopefully a theory of physics has actors. You can't say, I'm going to do physics with nothing, with absolutely nothing. So what are we staring at? What process, what mechanism, what event, what phenomenon, what's happening if there's no object? So the first word you need to define in physics is the word object. You need to know what an object is because physics cannot be done without objects. See how simple it is? And it says, if you absolutely insist, I will draw you a blob of ether. Yeah, draw it, please. But he didn't do it, so I had to do that. Okay, so what can I say? And the only thing I want to comment here is that, I put out there that fluid is made out of, the types of fluids that we know about, gas or liquids. And both of them are made out of atoms. Okay, so if he's going to say that the ether is made out of atoms, then we can talk about fluids. But hopefully he won't say that. He won't say that ether is made out of atom because he wants to say it the other way around. He says that atoms are made of ether. Okay, so then we need to find out what this ether is that he says is a fluid because fluids are all made out of atoms that we know of. And so he's got to redefine the word fluid. And he says something that flows. Yeah, but the something that flows is made out of atoms. So he can't just say something that flows. Because so far he hasn't mentioned what is the actor in his theory. He's just saying, I'm going to consider it like a liquid or a gas or whatever. And he wants to continue and say, let me tell you my theory. No, we don't want to hear your stupid theory. If you cannot present your actor, you have no theory. Okay? You have nothing to explain. You have no physics. You need that actor, what you call word salad, semantics. We need a lot of that. We need 150% of that. Okay, so put a picture there so we know what you're talking about and that we know what's moving on the screen, or we can visualize it or whatever. Okay, so here we have our astronaut releasing the blob again. Okay, and what we did the other day, we froze that. Okay, and you can see it. You can see it bigger here, and here we froze it. I think it's this one. Well, you can have the blob in different shapes. That's all I want to show here. You know, the blob can be very neat one like this one, okay, or you can have this irregular blob here. So it doesn't matter what blob you have. The question is, does that blob have shape? And someone might say, well, it's changing its shape. Yeah, we don't care. It doesn't have shape. It's a question of yes or no. Does it have shape? Okay, and people think that because it changes its shape from one moment to the next, this is the notion they have, it's not an object. It doesn't have shape. Or because it has an irregular shape, they say it's shapeless. That's the notion of ordinary speech. You can't use that in physics. In physics, it either has shape or it don't. Black or white. Okay, and hopefully that blob had shape. Okay. Okay, so what do we do with that blob? Well, we're trying to see if we can explain gravity with the ether, especially gravity. Okay, we can explain light as well, no problem. But above all, try to explain gravity, because that's what people have been searching for. You get that, well, you become famous. So here we have our spoon, talked about the other day. Okay, it's going to fall to the ground, okay? Now, there's only two possibilities as far as I'm concerned. One is that, you know, the blob of ether pushes on it, okay? That's one scenario, and I don't want to put words in anybody's mouth, okay? Here's the other scenario. The blob pulls on it from below somehow, okay? That's the other notion. And so you have to explain whether the blob pushes or pulls on the spoon, because, you know, that's what we observe every day. You know, here, you know, you let go of the spoon and it falls to the ground. So what we have to explain is what we call gravity, which is that process you just observed of the spoon always. It never falls to the ceiling. You know, it always falls to the ground. So we just want you to explain why it falls to the ground. Is the blob pushing on the spoon, or is it pulling from below? What is this fellow's answer? Well, he says the following. He says it isn't either one. It ain't either one. There is no pull. It's irrational. It's not push either. Okay? No push or pull. There's no other form of contact, of physical contact we know about, but he says it's neither push nor pull. So what is it? He says it's entrainment in the flow of ether. Okay? It only flows in the presence of matter, otherwise ether is inertial. So simple. Yeah, okay. So let's go with the first problem, entrainment. What is entrainment? Well, when you get carried by the river, it's called entrainment. And the question is, why does the river push you? I mean, the river is pushing you. All these molecules, but this guy doesn't understand that. He doesn't understand basic things like, you know, that little 5-year-old could understand, which is, you know, playing with blocks in kindergarten. He doesn't understand kindergarten physics. Entrainment is push. You're being taken. And he mentions a Venturi effect, which is the same. Why does a particle move from one container or whatever to another? That's what you got to explain. What causes, what brings it out? What pushes or pulls on it, because something is in contact with a molecule. Otherwise, you're using spirits and ghosts to explain that process. And they say it's a Venturi effect. Yeah, it's just sucked out. Sucked out by what? What is in contact with a molecule pulling on it or pushing on it? There's got to be some physical contact. There's only two forms that we know of. One is push and the other one's pull for something to move, right? Otherwise, it's known as, tug of war that nobody wins. But so entrainment is push. And there's no push. He doesn't understand squat. He doesn't understand what he's saying. But a lot of people think like him, and they say, oh, there's no push. It's entrainments of Venturi effect or whatever. Okay, and the other problem is, he says, ether is inertial. Unless it flows in the presence of matter, it's inertial. Okay, so please draw the inertial ether. That's what we want. We want to see a total picture all around the shape of the ether. Okay? The blob, whatever you think the ether is, a river, whatever it is, I don't care. But draw it. We want a picture. And it's very simple. I'm going to put the two atoms here, that you saw a minute ago, or two particles or whatever. And I want you to put, and you can take a snapshot of that or download the picture or whatever you have to do, with your computer. And all you have to do is, in that same picture, put whatever the ether is between the two particles. Now, that's as easy as it gets. I mean, I put a rope between the two particles. Quantum mechanics puts these waves. Sometimes they put particles. Okay, no problem. What are you going to put between the two particles? That's what we need to see. And we want a picture. We don't want blah, blah, blah. We don't want words. We don't want explanations. We want a picture. I don't know how difficult that can be. I'm going to give you the picture of two balls, which you can put cubes if you want, but I put two balls in there and I call them atoms, okay? And I want you to tell me what you're going to put between the two atoms. And the fellow says that it's the ether, and so he's got to put the ether between the two atoms. He's got to show us what he's talking about, okay? And that's the issue, and it's got to be all around. We need to see the ether all around, okay? You can't just say, well, it extends to the end of the universe, and I don't know what it looks like. You can't use it. We don't care what it looks like in reality. We want to know what's in your mind. We want you to pull your piece of your mind out, put it out here so that we can all visualize the same thing that's going through your brain. Okay, I hope that's clear. I don't know how much more clear I can do this, right? Another fellow comes over and he says the following. He says, nothing is pulling or pushing when something is falling, Bill. Gravity is not pushing or pulling. Okay, so I wonder what form of contact this fellow has going through his head, Okay, maybe you learned something new. He says, gravity is not pushing or pulling, it is accelerating. Accelerating. Okay, just because it wants to. It just suddenly decided to accelerate. I mean, when you accelerate your car, you're at least pushing on something, I think, the accelerator. But he says, no, here we do acceleration without any force, without anything. To push or pull something requires force, and gravity is the opposite of force, whatever that is. Okay, he should have put the word so we knew what he's talking about. But there you have it. Here you have the equation. Force equals mass times what? Acceleration. That means that acceleration is equal to what? Force, right? Divided by mass. It's not horse, it's force. Okay, so acceleration does involve force. So again, all these people need to take kindergarten physics. Okay, they've never gone through kindergarten, and they want to do college physics. Yeah, acceleration requires force, something to push. What is Newton's? One of Newton's motion laws says that something continues in its straight path unless something else, deviates it from that path. Okay, so you need force, you need contact, you need push or pull, but you need something there. And again, you can't use really the word force. You need to put a physical object there, and there has to be physical contact. Now, a rope contacts an atom, so I have a contact there, but quantum mechanics works with particles against particles, no problem, because you can explain push. But what quantum cannot explain and will never explain is pull. That's why they're still researching. They cannot produce the only force that half of the forces in the universe, which is the force of pull. Okay, so here we have our ether blob, other possibility. One was a little blob pushing from above, the other one pulling from below. Here we have the ether, that blob that's in the background. Well, imagine that's the inertial ether that he called, the static ether. So I froze it there, and it covers the universe. It goes all the way to the edge of the universe. And what he's got to explain with that ocean, with the whole ocean, he can't take a little piece of it and try to explain this, he's got to take the whole ocean, because ether is the whole ocean. If he's going to talk about something happening locally, he's got to use a different word. Okay, and there you see it. The spoons are falling, one from one side of the planet, the other one from below. They both go in the opposite directions. He got to explain it with his ether, how this phenomenon happened, how it is that one spoon goes in the opposite direction as the other, and both fall to the center of the earth. So this is what he's got to reproduce with his ether. And the ether, he can put it in motion if he wants, I don't care, but he's got to explain how that happens. And again, he can't use a portion of the ether, okay? Because this is, again, like you have the ocean, and something's happening to one fish in one localized area of the ocean. You cannot say the ocean pushed the fish downwards. You can't do that. Something else happened, because it didn't push the boat or something else that was in the ocean. It just pushed that little fellow, that little fish downwards. If that happens, it can't be, you can't say the ocean did it. The ocean is the whole thing, the whole shebang. You got to say, look, a little piece of the ocean. And now we have to talk about that little piece. What are you going to call it? What is it? You know, now we're talking about something else. Forget about the ocean now. So you can't use the word ether to produce that effect. Now you have to use whatever you want to call it. In the case of the ocean, you say, look, a little bit of water. There was a whirlpool or a current or something affected the fish. Okay, fine. But now you're talking about, you know, some water locally. Water is a physical object. It's a fluid, right? It's made out of atoms, out of molecules, right? So water is a physical object. It's a thing. That's why it came in contact with a fish and pushed it down or pulled it downwards, whatever. So you can explain it with water, not with the ocean. You can't say the ocean did it. And that's what you're doing when you say the ether did it. Okay, so let's understand. Ether is the ocean. Otherwise, we got to look at what I just showed a minute ago, which is one little blob of ether pushing the spoon downwards, or another one pulling from below. And you got to explain that process. You got to show us how the ether did either one. And yeah, you can only use pull and push, but he says he doesn't believe in pull and push. He says it's entrainment, which is push. But he doesn't understand that either. He doesn't understand what the Venturi effect is, or how it happened, what causes the Venturi effect to happen. I mean, I worked with vacuum many years, and vacuum chambers. And, you know, we have vacuum pumps. They're known as the roughing pump, the mechanical pump. A rotary vane pump is also known. You have this little paddle that goes around inside the pump, and it just takes molecules from the chamber, right, that drift in that direction, and it takes it out, and then the next pedal takes another group of atoms out, another group of molecules, etc. And this way it sucks air and water and other garbage that you have in the chamber. It sucks them out of the chamber and creates a vacuum. Not a total vacuum, but it makes a greater vacuum. Roughing pumps go to 10 to the minus 3 torr, and then you can take a cryo pump or a diffusion pump and pump it down to -7, which is the range where we worked with. The question is, this is the $1 million question, why does a particle go in that direction? What's drawing it in that direction? In other words, why do particles move from a area of great density to an area of lower density, or a vacuum? That's what you got to explain. And people say, it does so, it is so. Yeah, we know it is so, that it happens. You have to explain the cause, the mechanism. What is in contact with a molecule? Is there someone whispering the molecule's ear and say, go that way? Why does the molecule, what causes, what physical cause forces the particle to go to the region of lower vacuum? That's what you got to explain. And people say, it does so, it is so. Yeah, we know. Don't tell me it is so. Tell me how come it is so. And if you cannot explain the how come, don't talk to me about the Venturi effect or about all the other nonsense that you get in your head. Okay, because it means you haven't gone to kindergarten physics. Okay, Okay, here we have another fellow. Oh no, the same fellow, the first one, right? And he says he backtracked and he said, the ether being a bunch of particles, that's your opinion. Okay, so it ain't a bunch of particles. I don't care for what they thought hundreds of years ago. Okay, so he doesn't care about Aristotle, the Greeks, or 19th century. Said, what's in between atoms? Yeah, that's what we're asking. And he says, it's the ether. Okay, so now we had two atoms, which I showed, and I want him to put the ether, the static ether, the inertial ether, whatever he wants to call it, so that we can see a picture of the ether. How else would they attract or repel each other? Exactly. So show us the ether, show us how the ether does it. And he says, I can't point to magnetism, but it's there. Yeah, you can't point because you can't see or feel it with your hands. And you're saying it's there. Yeah, but what is it that it's there? That's what you got to identify, the invisible object that is in that region we call magnetic field, right? And same thing for the ether. It says, I can't point you to ether, it's invisible. It's got nothing to do with visibility or with tangibility. It's got to do with the ether having shape or not shape. And we need to know what shape you're thinking about, what shape you're visualizing. And I want you to make it visible for all of us so that we can follow your train of thought. See how simple it is? So yeah, it is simple, but you're not doing the simple stuff. And yes, ether is space. Okay, so he's saying it's the same thing as space. As for the ether blob, it was a joke. Okay, so I explained it with the blob, but now he's backtracking after I called his bluff, and he says, look, I was just joking. Okay, no problem. And I'm saying he's not joking. He's really not joking because a blob is what he described. He says it's a fluid that is flowing, flowing fluid, flow flu. Okay, so we have a flow flu. That's what we'll call his ether, and we need for him to illustrate the flow flu. Okay, so he was talking about a blob. A river is a blob. An ocean is a blob. So is the air that covers the earth. All those are blobs. So if he says the blob, the ether is fluid and it flows, he's talking about a blob. So he was not joking. The joke's on him, or the yoke's in his face, whatever. It's fluid. Yeah, if it's fluid, it's a blob. Dynamics, magneto, whatever. Any substance that flows is considered a fluid. Okay, great. I've been working on this for many years. I won't go through the entire process. It would lead me to my conclusion. On the one hand, I feel sorry for the guy because I'm sure he has been working on it for a long time, but he hasn't taken care of the basics. He hasn't taken care of the ABCs. He hasn't done kindergarten physics. Kindergarten physics, identify the object. You need to do that. And he never did. He just said, oh, it's the ether. And he didn't use the ether of the Greeks or the 19th century, all the way to the 19th century, which is a bunch of particles. He's got some other theory or some other vision of what the ether is in his head. No problem. He wants to use the word ether to refer to his blob. No problem. But it's a blob because he's talking about a fluid. And that means the fluid stops somewhere. Somewhere it's got an end. Otherwise, it's not an object. You can't have an eternal or constantly flowing fluid that comes out of nowhere. Okay? It's got to have total shape. We got to see the whole shebang. I want you to draw the ocean. That's what we need. We need the whole ocean. Okay? So if you say ether is the same thing as space, it extends to the edge of the universe, draw the universe for us. Don't leave that hanging out there, loose ends, saying, I don't know where it ends, and I can't see it, and I can't touch it. No, that doesn't count in physics. In physics, you have to present the object so that we can see the process, the mechanism that you propose for gravity, or how particle attracts another, whatever you want to call it, entrainment. Okay, it entrains. Okay, so entrain it. Show us how the mechanism of entrainment, that's what we need to see in detail. But before that, you need to illustrate your ether because otherwise we will not understand. And I'm going to put the two atoms there for you to put your ether between them. So, the ball is in your court. And what this fellow says reminds me of something I read the other day. And here, he'll probably relate to this very easily, and so will everybody out there. And here it is. This article came out on space.com. We still don't know what dark matter is, but here's what it's not. Okay, and this is what they say, the relevant part. Even though scientists are certain that dark matter exists, as all our universe's normal matter simply can't account for the way galaxies are kind of held together, they don't know what it is. They also don't really know where it is, though they have some ideas, and they definitely don't know what it looks like. And that's what this guy is saying. He's saying, look, the ether is there. I know it's there. I've seen it. I've touched it. I've pointed to it. Or he says, it doesn't have shape. I can't see it. I can't touch it. I can't, point to it. And he's saying the same thing as these people. He say, oh, we can't account for dark matter because we can't see it and we can't smell it and we can't hear it. And so they go with all these excuses, but they know it's there. It exists. So this is the way all these people work. And no, that's why we say, look, that doesn't work that way in science. The way it works in science is the other way around. You tell me what the dark matter is, then you can talk about it. But don't say, it's there, we know, we proved it, it's there, there's no other possibility, and we're not going to allow any criticism, and let me explain to you my theory. No, it doesn't work that way in science. In science, it works the other way. Okay, you got to point to the dark matter, and then say, look, with this dark matter, now I can explain, how a galaxy rotates, or why the stars don't fly away, or whatever. Okay, that's the way it works. And you got to make whatever's in your mind visible so that we can follow your train of thought. They don't do that. What do? They talk about mass and gravity. They use concepts. They talk about field, energy. We don't want to hear those words. We want to see objects. I want to see a dog. I want to see a cat. I want to see a rock. I want to see a tree. I want to see something. I need to see the physical interaction between objects, things. That's physics. But to say that the mass did it, how did it do it? Did the mass, the concept mass, pulls or push? How did it do it? And so this is the problem. They use concept. And this fellow is doing the same thing with the ether. He's saying, I can't see it, I can't touch it, so I can't draw it. No, tell me what you have in your mind. I don't care what the ether is in reality. I want you to draw the ether that you have in your mind and show me how it is between two atoms. Very simple stuff, really. Okay, so here we have our two atoms again, okay? And what I'm going to ask him is to put the ether that he's got in his brain in between those two atoms instead of that question mark. That's what he's got to do. Very simple. You have two atoms, okay? He wants to put cubic atoms, triangular atoms, I don't care. He can put whatever atom. I put two balls, okay, or what appears to be two balls, okay? So all he's got to do is put the ether between them. He says the ether is between two atoms. I need to see it between them. And he says the ether extends to the edge of the universe. He's talking about an ocean and not about what attracts one atom to another, which is what he's got to explain. So then he's got to figure out, how he's going to do this. Okay, so since he hasn't done so, I try to do it for him. He says it's a flow flu. Okay, so here we have the flow flu. Okay, we have the ether flowing from one atom to another. Okay, so we have the flow flu. That's what we'll call it. The ether is the black stuff that extends all the way to the edge of the universe, no problem. But the flow flu is different than the ether, or it's a portion of the ether, or he's got to explain what that flow flu is. And you can see it's flowing. I put a river. I even put the fishies in there for him. So, if you can't understand this, I don't know. So you can see the river, or this flow flu, is flowing from one atom to the other. How does that produce attraction? How does that get the two atoms to come together? Because if it's flowing in one direction and one direction only. Okay? And so there you have it. That's what he's got to do. Now, I put another type of flow flu, and this is my flow flu, the one that I proposed for him, and that's a spirit, a ghost, one of Casper's friends. And he might say, well, you're making fun of my theory. No, I'm not. I'm illustrating what you describe. I have something which is fluid. Okay, it's called a ghost. It's called a spirit, an angel, whatever you want to call that. And you can see how it's flowing. So you have your flow flu there. Okay, so don't tell me that I'm making fun of your theory. I'm illustrating what you failed to do. You don't like my flow flu? My ether, then you put yours in there and show us how one atom attracts another with your flow flu. Okay, so that's what you got to do. Very simple stuff. And it's here you see it. Okay, this is what you got to do. You got to point to the ether. said it several times. I need for you to point to the ether, put a picture there, right, between the two atoms. You say the ether is between two atoms, we want to see it. I want to see what you're talking about, okay? And if you can't, then it means you haven't imagined your ether. You're just talking, out of because the air is free. Okay, so here we have okay, I see what. Give me a second here. Here we have kindergarten physics again. So we have the scientific method. What's the first thing he's got to do? He's got to present the objects. He hasn't gotten past that step. He hasn't presented the object yet. He wants to jump all the way to theory. He wants to tell us his theory. And we don't care about his theory until he can present the object, because if he cannot present the objects, if he cannot point to them, his theory is bunk, it's garbage, it's worthless. So we don't care about his theory, okay? We need the objects, then he can move on to his theory, okay? And here we have another fellow, and he butted in. He wanted to talk about the ether, his ether, okay? And this fellow says that the ether is two particles. Okay, he says, I have a hypothesis that can logically explain what could be referred to as the ether. Hey, great. My hypothesis is that everything that exists in the universe is composed of just two incredibly small monopole particles. Okay, these particles are what is referred to as the ether. Okay, so there you have it, folks. You always want to know what the ether is. There you have it, two particles. One is negatively charged, whatever that is. The second particle is positively charged, whatever that is. Okay, we don't care about negative or positive because that's garbage. It's nonsense, poppycock. Okay, they don't belong to physics. We don't know what negative or positive mean in physics. There is no definition, no object that you can say, oh, that one's negative. Unless you're talking about women and men. Say, women are all negative, men are all positive. Here, my wife will kill me tonight. There exists a massive excess of the negative particles. Great, that's a description. You haven't explained anything with that. And accounts for the force of gravity. Okay, great. You have to show us the mechanism, okay? And again, what's the problem here? The problem is you cannot say that's the ether, because two particles do not an object make. There we have two objects, okay, two balls. Okay, so you got to explain it with one ball, okay? You can't explain it with two balls. But if you need two balls to explain your theory, no problem. You present one, say, look, this is the red ball, this one's the blue ball. You want to make them green and yellow, positive and negative, whatever that means. We don't care. We have two balls. Take a basketball, you take a snowball if you want, okay? And then show us how one snowball or one ball or one tennis ball or baseball attracts another. That's all you got to show. Pull. We want to see the force of attraction, how you explain attraction especially. Okay? That's all you got to do. Show us your two particles, show us how they're attracted by this ether or whatever. So don't use positive, negatives, don't use the word field, the word energy, the word mass, none of that counts. We need physical objects. We just need a movie of how one particle attracts another. Very simple. We want mechanisms. And I don't have that sunk in. Okay? Another person comes in and says, what? Ether is electric, resulting of rotating magnetic field. Well, the problem is field is a concept, and concepts don't rotate. So that's the end of that one. So I don't know what this person drank, okay, but says that field rotates. No, fields don't rotate because field is concept. Love doesn't rotate. Love doesn't attract either. You can't do it with love. I tried pulling on a horse with love. It didn't work. He kicked me. Okay, and then we had people here who were working on the word object. And I said object is that which has shape. And these people got all hung up on shape, so I had to, correct them, and I did that last week. But the fellow didn't come back with any criticism or analysis or challenge or anything. So I guess either he accepted what I proposed or had no counter arguments and just, went to the deck. Okay, so here it is. He raised the issue. Shape is 2D and form is 3D. Object is a collection of matter, and magnetic field has shape. Those were three of the points he made, the main ones. And these were my answers that he failed to address. Other languages only have the word form. They don't use the word shape. Okay, the word shape is primarily English, maybe uniquely English. All other languages just use the word form. And you can see why, because even in English, shape is a synonym of form. Okay, and here you can see the definition. I presented that the other day of both shape and form. And you can see that they're perfect synonyms. There is no difference between shape and form. Form does not refer to 3D. Shape does not refer to 2D. Okay, this is a misconception that people have out there. That's just ordinary speech that people come up with these notions. That's not true in the definitions in the dictionary, even if that were important, which it ain't. Okay, but you can see shape, the quality of a distinct object or body in having an external surface. Surface is a 3D concept, and so we're talking about shape has to do with 3D. Or outline or form, what? Outline of form or figure. Okay, this quality is found in some object or body form. Outline, silhouette, etc. And what is form? External appearance of a clearly defined area. Area is what? 2D, right? As distinguished from color, material, etc. Okay, the shape of a thing or person. Okay, something that gives or determines shape. Okay, so you can see that shape and form are perfect synonyms, even in English. But in other languages, they don't have the word shape. They only have the word form. So yeah, this poor fellow, you know, he didn't come back. He didn't answer the questions, and so I guess he agreed or just ran away or whatever. It didn't address the issues that were raised. Okay. And just in case, here's another fellow, and he made the same error more or less, says a shadow of a ball has shape. No, shadows don't have shape. That's in ordinary speech. Okay? And again, people haven't taken kindergarten physics. The ball itself has form. Okay? Does the shadow have form? Yes, because shape and form are synonyms, first of all. Second, a shadow does not have shape. Okay? That's in ordinary speech. Shape, shadow, why doesn't it have shape? Because it's light. We're talking about light. If you take the light away, and you need three objects, actually, the light, the object, the tree, and the shadow, right? But you take the light and the tree away, and there is no shadow, okay? And I want you to do this experiment next time at home, okay? Always in the presence of a relativist, right? Because it's a dangerous experiment. You take a flashlight, right, and a tree or at night, you know, and you can create an umbra or penumbra or whatever. Or you can do it during the day. You can have the sun or whatever, or you can have even a very bright light, right? Create a shadow with some kind of object. Then take the object and the light and the source of light, right, to outer space and tell me what kind of shadow you see out there, okay? And you'll see how the shadow disappears. It has no shape whatsoever. Yeah, all holograms, shadows, all those are not shapes. Okay, shape is what an object has all by itself, without the help of anything else. Okay, and I always give that analogy where you have the angel with a little plate or the ring on its head. Without the angel, that's just a ring. If you want it to be a halo, you need the angel. And therefore, you can see the difference between a ring or a plate on the one hand and a halo on the other. Halo requires the angel. Without the angel, all you have is a plate or a ring. And it takes a long time for these people to understand it because they haven't gone through kindergarten physics.